Hi, everyone. Welcome. This is Diana Sinton, the Executive Director of UCGIS. We're excited to present this webinar today about the new National Coordinate System that we're all going to be working with sooner than we might be ready for otherwise. This is one of the first webinars in our 2021 series. We're excited to be offering many this academic year. We're going to get started in just a minute. As I know, sometimes many people are just joining us right now. We have a very large number of attendees that we're expecting, and people are just continuing to log on, so we'll wait another 30 or 45 seconds before we start the presentation itself. As a reminder, in this webinar system, your microphones will remain muted throughout the presentation. If you have questions, and we hope you do, please feel free to write them into the chat space, or I'm sorry, the question space. Each of you has a question space with a little question mark icon. Please use that question space to record questions for the presenters, and we will have a little bit of time at the end of the session today, and questions that we aren't able to get to, we will respond to afterwards. If you have technology questions, feel free to put those into technology related to GoToWebinar, not to other technologies we use. Put those into the question space as well, and I will try to address any GoToWebinar related technology questions in the moment. Some people, if you have audio issues, look under your audio setting to confirm which speaker the sound is expecting to come out of, because 95% of the time that's the situation to troubleshoot your microphone, or not your microphone, your speaker problems. Some people find it successful to just exit the system and then come back in. With that, now that we're a couple minutes past the hour, I am very pleased to be able to introduce this topic and our speakers. Ed Carlson is going to be sharing with us today, and Dr. Michael Dennis is also here as one of the other people who's going to be able to answer some of our questions. So with that, Ed, I'm going to mute myself and turn it over to you.
Okay, thank you. Aloha, everybody. Can you hear me? I hope you can, and good day. We're going to be talking about this new topic that's coming up that Ms. Kemp asked me to talk about the new datum that National Geodetic Survey is working on. So what is the National Geodetic Survey? Well, we're the oldest scientific organization in the United States. We were chartered by Thomas Jefferson in 1807, and we were called the Coastal Geodetic Survey for many years, and then in 1970 we became part of NOAA, and then we were called the National Ocean Service then, and then we became part of that, and we call it National Geodetic Survey. With that, like I said, we're in the Department of Commerce. We're not in the Department of Interior. A lot of people mistake us for the USGS. We are not the USGS. We are the National Geodetic Survey, and USGS makes maps, and we define the National Coordinate Reference Frame. That's our main mission, is the National Spatial Reference System. And it is to help our national economy and social and environmental needs. We do a lot of work with the FAA and airport surveys. We do a lot of navigation work for the nautical charts. We do a lot of work with surveyors, private industry. We do a lot of work with precision agriculture, and we do a lot of work through our continuing operating reference stations for people who are doing GIS work in the country. So what is the role of the National Spatial Reference System? It's the official coordinate system for all geospatial work to be done by non-military federal government. That's latitude, longitudes, and this is mandated by federal registry notice of what the datum you'll be using and what information is. So if you ever do any work for a federal government agency, it'll require that you work on the National Spatial Reference System. In that, we have what we call a geodetic datum, which is an abstract coordinate system with the reference system, such as the NAD 83 2011 or Guam Vertical Datum of 04, which is a vertical datum. So these serve as datums that provide our known locations to begin surveys and create maps. Geodetic control is provide a common reference system for establishing the coordinates for all the geodetic data on the datum. And all the National Spatial Data Infrastructure Framework data users are required now to use geodetic control for accurate registration of their geospatial data. The NSRS has evolved over the years. When we first started off in 1807, we used to have a datum called the US Standard Datum until 1927. And you can see that the accuracy of the network accuracy was greater than 10 meters. Then in 1927, when we did a readjustment and surveying was getting a little better than it was over the years since 1800s, we had the data, we say the network was accurate to about 10 meters. And then advent of GPS and all the new modern technology that we've had over the years in the NAD 83 2011, we're saying that the accuracy is down to a centimeter for the network. So that means is that the relative accuracy from one point to another, we can get better than a centimeter. Horizontal datums. These are the parts of the National Spatial Reference System we talk about. You probably, if you're GIS users, probably know about. We talk about the old NAD 27 or the NAD 83 now, and all the vertical datums that we have. We have the old NGVD 29, which was a sea level tidal-based datum, which was developed off tide stations across the country. And then we had the NAVD 88, which is a single point vertical datum with founding point is Father Point Rimouski in Canada, just across the border. And these are all the geoid models that we use. Now, over the years that we've developed them, they're getting better and better with technology from first when satellites surveying started. These are not part of the NSRS, and we get a lot of calls about it. Well, I have WGS-84 coordinates. What do I do? And we say, well, we're not responsible for them, but as an advisor, I know a lot about them. And when I ask people that, I ask them, well, what WGS-84 are you working on? Because there's 5 different or 6 different epochs now, and that kind of slows them down a little. But this is something to be known that the NAD 83 and the WGS-84 are 2 different datums, and they're not aligned with each other right now. So what happened over the years when we had GPS and we had the NAD 83? We had to determine where the center of the Earth was. We had to come up with some value and say this is where the center of the Earth is at the best that we knew in 1983. But since then, with advent of satellite surveying or GPS, that we know that we are not exactly at the right spot, and we have this international terrestrial reference frame that's used by everybody, by the whole world, as the main reference frame for the world. And we know that there's an offset between the NAD 83 and the ITRF of 2.2 meters. So we have to take care of that problem that we know that we have, and we want to adopt our new datum to be in line with the ITRF. And the other thing we have a problem with is we know that we have continuing operating reference stations, which we call CORS. We have 22 to 2300 across the country and in the territories. And these are marks that are permanently mounted, and they're collecting data 24/7, 365 days a year. And we can see that we know that there's a movement in the Earth, and it's changed, and we can see what it is reference to the passive marks. So now we have the CORS data and the passive marks. They're not aligning right, so we want to get everything aligned to each other. And of course, why I've been saying, why are we doing this? Why are we replacing the NAD 83 and the vertical datums? Of course, it's a global navigation system. What did I do? I messed up. Sorry about that. Operator error. Access to the GNSS is fast and inexpensive now with GPS. I mean, when we first started doing GPS, back in the 80s, the first GPS receiver cost $110,000. Now we can get a receiver that is more accurate and faster and will do the work for less than $1,500 to do surveying grade work. It reduces reliance on finding survey control because a lot of our survey marks that we have across the country that we have been destroyed by road work or anything, construction, or people just taking them. Accuracy. This is the most important thing because it's insensitive to distance dependent and it's reliable. In other words, what this means is that when we had to do the work back in with surveying, traditional surveying methods, we could only go as long as the line of sight. Now we can have a GPS unit, GPS unit on a station in Colorado, and we can have another one on the station in San Diego, and we can determine the distance and get the coordinates independent to each other with very little time. We could do that probably within 5 to 6 hours. And of course, it's immune to benchmark stability. In other words, if its benchmark is moved due to science, we can see that using our course sites. Consistency eliminates the systematic error in all the current datums, which we have by using surveying equipment. You have systematic error and random error, and this helps eliminate systematic error. It aligns, like I said, this is going to align ourselves with a global reference frame, and it's an integrated system for both position and heights and elevations. Now we have a system, we're working with a system where we have to do the horizontal and then we have to do the vertical using leveling, and those are two, and that's a very time-consuming proposition. With this new system, we'll be able to go out and do GPS observations, be able to get a good position and good orthometric height. So we know we had these problems and the shortcomings. So back in 2013, NGS came up with a 10-year plan, and part of it is to support the National Spatial Reference System, modernize and improve the NAD 83 and the NAVD 88, expand our stakeholder base through partnerships and education outreach, and this is one of the things I'm doing is the outreach now. Develop a workforce that can support our environment and improve the organizational administration function of NGS. But what we're going to talk about is replacing the NAD 83. And by 2022, we want to be able to go out and do observations using a survey grade GPS receiver, and with less than around 30 minutes, we'll be able to get 1 centimeter accuracy to the reference frame. And also with the vertical, we want to be able to get 2 centimeters when we use 30 minutes of GNSS data. This is now, I said, a survey grade receiver, and that's one that has L1, L2 functions. And we're going to also provide the tools to easily transform between the old and the new, or new to the old. We can go either way. So what's going to happen is we know that the Earth's moving in different ways and the plates are moving differently. When we had the NAD 83, we assumed that everything was the same. So the observations for North America were the same. We're using the same information for Hawaii and the Pacific and Guam and American Samoa. But now we know that through the advent of the GPS and studying this, that we have the 4 plates. So we're going to have North American terrestrial reference frame. We're going to have a Pacific terrestrial reference frame. We're going to have a Caribbean and a Marianas, or they call it Mariana terrestrial reference frame. And all these are going to be separate, but we can go from one to the other. We'll have ways of moving from one to the other for you. So the guiding principles for this whole new surveying system we're going to come up with in the 2022 datum is that we're going to use continuing operating reference stations. Are going to be our foundational part of the component of the datum. We're going to align everything to the International Earth Rotation and Reference Service, or the ITRF reference frame, which is a worldwide standard that's used by all the countries. And we're one of the members, and we supply information to support that through our work with the International GNSS service and our reference sites. We have, I think, out of our core sites that we have, 2,500 core sites, I think 15 or 20 of them are using this reference frame, or the ITRF, the GNSS service. And of course, NGS will continue to be defined in relationship to the ITRF. So the ITRF is going to be our base of our new datum, and then we're going to be able to define our plates, our 4 plates off this ITRF system. So here's a map of where we're thinking of the tentative foundation cores are going to be used. These are going to be the ones that are going to be the base, and they're going to be the ones that we're going to hold fixed for all the plate movements and all the observations that we're going to use for the 2022 datum. Now, we will adjust this if we find out that there's movement in these cores over the years. And we're thinking that we might have to change this tentatively. We're thinking of maybe a 5-year or a 10-year change. Okay, what's this going to mean to you? Well, as a GIS user, all the coordinates and heights are going to change. So how much are they going to change? Well, this is an approximation of what we think they're going to change, or we're pretty close. This is what they're going to change in North America. So we're going to go from, in the North America plate, it's going to be from 0 meters to 2 meters in positional change. In the Pacific, with the Pacific plate, it's going to be a low of 2.3 meters to 4.3 meters. So you can see that if you're going to be doing work out in the Pacific, you're going to have to take this into consideration. And in Marianas plate is going to be 1 meter to 1.4 meters. Also, I said that the service is going to give us a height, ellipsoidal height. And this is going to be the change, and the ellipsoidal height is going to be from -2 meters to a high of 2 meters. So you can see that through the CONUS, or North America, it's going to be mostly negative values. It's going to go down. But when we get out to the Pacific, we're going to be in the positive changes. So with this, how does a geodesist, who I am, view the world? We view it as 3-dimensional, and we have different elements to go together. And this is how we get orthometric heights, or heights using GPS. First, we have our geoid, or our WGS-84 ellipsoid, and that's the defined. These are defined, and every time we use them, if you say GSR 80 ellipsoid, they're set defined factors for the semi-majors and semi-minor axis and the flattening. Same with the WGS-84. And the difference of them is very minute. I mean, very minute. It's difference in the semi-major axis. I think it's 1 in the 5th decimal place. Now, this is one thing that's confusing for a lot of people, is that the WGS-84 has an ellipsoid, and it also is called the WGS-84 datum, where in the NAD-83 or the 2022 datum, we're going to use a GSR 80 ellipsoid. So what we're trying to do is we're trying to find a height on a topographic surface. And this is going to be our orthometric height, or NAVD-88, or local main sea level height, or it could be a Guam vertical datum, just the height, the orthometric height above the surface. So we know we hit the ellipsoidal height. From GPS, we'll get the ellipsoidal height. we get latitude, longitude, and ellipsoidal height. We know that value. But we don't know the geoid height. The geoid height is a height that is the equal potential level surface, which best defines the least squares since the global mean sea level. This is global mean sea level. This is not mean sea level. And the way we get this and determine this is we do it through modeling. So this is a model that we've developed over the years. And when we get more and more gravity data, we can make the model more accurate. So now we're using model geoid 12A or 12B. And if you're outside the CONUS and outside the United States, you'd use EGM08, which is a model that's developed by the DOD. So with this, we can determine the height, and that is the ellipsoidal height minus the geoid height. Now, this is very important to remember. You have to watch your sign convention. So your sign convention is in the United States or CONUS, height is value is a minus. So really, to determine orthometric height, it's a minus times a minus makes a positive, so you're adding. But in the Pacific, it's going to be just a negative. You're going to take the ellipsoidal height and subtract the geoid height. So what's the problem, and why can't this work? Well, we know we have problems because we have the GPS. We get like I said, we can get the good ellipsoidal height, and then we have a geoid model. So what we have here is the problem we're finding now is that we have a GPS orthometric height to a certain point on the mountain, but we have a leveled surface, which is the NAVD88, which was done through leveling before GPS, and we have this elevation, but we know that this height's above mean sea level or NAVD88, but we have this difference. And in the CONUS, we have an error of about 50 centimeters average, but we have about a meter tilt from coast to coast, from the east coast to the west coast. And in Hawaii, we have this is that if we use the GPS and we go against the leveled observations that we have from the tide stations that we have, we'll have a difference of 50 to 70 centimeters. Well, that's a big difference. And if you're using the GPS to do, say, a floodplain map, you're going to be in problems because you're going to be off by 50 to 70 centimeters. And the average in Alaska is 1 to 2 meters. So to give you an example of what I'm talking about, I have the station Ben in Honolulu, and we use a geoid model 12A, and we got the ellipsoidal height of 21.09 meters for the GPS, and the geoid value we have is plus 15.196 meters. So subtracting that, we come up with 5.32 meters. But we know that through leveling from the tide station, that the elevation of that station is 5.894. So it's approximately a difference of 57 centimeters or 1.8 feet, which could make a difference if you're out there using your GPS and you're trying to do a floodplain certification, because you could put somebody in a floodplain or take them out when they're really in the floodplain. So how are we going to handle this? How are we going to take care of this problem? Well, we've come up with this gravity for redefinition of American Vertical Datum, what we call GravD, and we're going to change from a level-based system to a geoid GNSS-based gravimetric vertical datum. So we're going to be able to do this, and we want to be able to do this where the orthometric heights will be accurate to 2 centimeters. So there's 3 things we have to do for this project. One is airborne gravity survey of the whole country and its holdings, long-term monitoring of the geoid change, and we do that through setting up stations, and we just monitor them through gravity observations that we have, just like cores. We'll just monitor them over the time, or we'll come back every year and reoccupy them to get the gravity values through a real expensive and high precision gravimeter. And we're working with partner surveys through with DOD and USGS. And we're also going to hope to work with USGS to get their magnetic measurements, and we're on that now. So what's the extent of the new geoid model? Well, this is it. We're going to be from pole, or from south of American Samoa to the pole, and then we're going to have our areas in American Samoa and Northern Marianas. So we're going to have the Pacific from the equator up. Big area. A lot of flying we have to do. Now, we're not flying gravity over the ocean. We're just flying gravity over the US and a certain distance from the coastline. And same thing with American Samoa and Northern Marianas. The area that's blocked off is approximately the area that we're going to be flying. So what do we expect for the change doing this? Of course, we had one in the horizontal and the ellipsoid, and this is what the change we're expecting for the CONUS. So you can see that we're going to have minus 2 meters down in the panhandle of Florida to minus a meter up, say, in, I guess that's Portland, or a little north of Portland in Oregon, Eugene. So this could be a big difference, especially if you're doing shoreline mapping in this areas, that if you're doing trying to determine sea level rise and the change in it, or doing a floodplain map, you have to take this into account. And we're working with FEMA on this, so when they'll be developing new floodplain maps. But that's their responsibility, not ours. We're just going to help them, give them the information, and then they're going to do that. All right. So what do I do with historic maps and charts? This is what people ask me all the time. First one is the accuracy expected to be better than a few meters? If it isn't, then stop. You don't have to do anything. You won't gain anything by doing a transformation. But if you say yes, then next question you have trusted metadata, which puts your map and chart in the NSRS. If you don't, and you can't say what it is, how your map was developed, really your transformation tool will only work if it's in the NSRS, because you have to know what datum you're in to go from one to the other. If you say yes, then you want to use this program called NCAT, which is a program that will update the datum from one to the other. So this program is a conversion and transformation tool. And as you can see, we can go from the US standard datum, and we'll be able to go all the way around to the 2022 datum. So if you had UTMs in the US standard datum, it'll take it and convert it, and you wanted to come out with 2020 UTMs on the 2022 datum, it'll take it and it'll convert the UTMs to latitude, longitudes. We'll do a conversion, then it'll transform the coordinates from the US standard datum to the 2022 datum, and then convert them back to the UTMs. And this will all be done behind the scenes for you. We have a program that does it. And the program, like I said, is called NCAT, and what you have to do, it's on our web, it's free, it's interactive. You can do a single point, or you can do multiple conversions. I put 1 point in Honolulu to do it, and what it has is it has a drop-down menu, and you can see that you can choose your datum, your input datum, and I chose the old Hawaiian datum, and you can go to your output datum, and I got them backwards. I chose the PA11. I wanted to go to the old Hawaiian datum, and you can put what datum you want. So you go old Hawaiian to NED 83 PA11, or you can go from PA11 back to old Hawaiian. So what you'll get is your
Ed, we might have lost your audio.
Uh-oh.
Oh, there you go. You're back.
Okay.
What
Okay.
we heard you up through. What you get is
to this slide.
Yeah. Yep. The current slide where is transform coordinates. That's
okay.
Yep.
I'm sorry about that.
No, it's okay.
What I was saying is that you'll get information as you get the input coordinates, and then you get your output coordinates, and what the total change is in meters and in seconds, and what the accuracy is. And also what it'll do is it'll convert the coordinates to state plane coordinates or UTMs for you. You'll get both of those. So you get everything you need. And if you don't know your state plane coordinate zone and you have latitude, longitude, the program has a map, will figure it out and tell you your zone. But you could change the state plane coordinates, and also you can change the UTM zone. So if you were sitting on the boundary of one zone to the other, you can change it to whatever zone you want. So map projections. With this, we have information that we've come up with, and we've done map projections, and we have what we call the state plane coordinate system. And we know that surveyors can't work on a three-dimensional system. They like to work on a plane. They like to work on a flat system, just like the GIS users like to do, is they like to be on a flat system or on a table. So in 1935, or 33, we created this thing called the State Plane Coordinate System of 27. And we have them defined for the whole country, and they're different zones. As you can see, for CONUS, the breakups, like in Oklahoma, you can see that there's 3 different zones. In Texas, there's 5 different zones. California, I think it's 6 different zones, but you can see the different zones that we have and how they're defined. And then in when we did the NAD 83, we also developed state plane coordinate zones, and then we kept the same, almost the identical zones that we had in the 27 to make it easier for the surveyors. But as you can see, in Hawaii, we have 5 zones. Guam only had 1 zone. American Samoa only had 1 zone. And from this, we're going to go now move to the 2022 state plane coordinate system. But before we had this, we had distortion. And what this program did is we would develop these coordinates, and they were developed off the ellipsoid. So we were doing everything off the ellipsoid. So we'd have distortion, and if you were below the ellipsoid, your grid distance was less, the ellipsoidal distance, and if you're above the ellipsoid, your grid distance was greater than the ellipsoid, which is basic projections. But now, with the new state plane coordinate system, it's going to be referenced to the 4 reference frames, the ITR, what we call the Pacific, North America. It's going to be based on the same reference ellipsoid as the state plane coordinate system of 83, GSR 80. And we're going to use the same 3 projections: Lambert conformal, transverse Mercator, and oblique Mercator. But with this, we're doing a little different. We're changing things up, and we're taking this and we want to minimize the distortion. So we're going to have everything at the topographic surface, because that's what surveyors want to work at. They want to work at the topographic surface. They don't want to work at the ellipsoid. So this is to reduce the projected grid distance to the actual grid distance. We want to make this smaller. And Michael Dennis, the other person online, he's the project manager for the state plane coordinates. So what are we talking about now? So what we're going to do is we're going to do a projected surface, and we're going to bring it up as high as we can to the regular surface, and we're going to try to make the ground and the grid distance the exact same thing. But in some areas we have a problem because you have different mountains, you have mountains areas. So we're going to have to change the projection axis to be able to get these ground distances, as many ground distances as we can, to 1. So the only way to do this is, like I say, is the distortion is change the axis of the location. And this design is the same approach being used in the state plane coordinates to minimize the distortion with topography. So more about this is how we're going to do the projections. But also what we've done is we've come up with a new thing, as we said, we're going to have a statewide zone for all states. If you notice in the 27 and the 83 state plane coordinate, no, we didn't have all the states have the zones. They had different zones. So we're going to also keep the default zones if necessary to ensure that all states and territories are covered. So we can have a state, we'll have a statewide zone, plus they can have default zones. And the reason for this is that statewide zones will help the GIS users for GIS projects going across the state. And in Hawaii, this will be a big help because right now, if they're doing any work in UTMs, the state's divided by 2 UTM zones and 1 island's divided by 1 UTM zone. So if they decide to use 1 UTM zone for the whole island, they can distort the other part of the island. So this will help take care of the distortion in the mapping for the GIS users. And the surveyors, like I said, they like lower distortions for mapping and surveying when they're doing their work, because they work in smaller areas than all this whole state or a county. They work in project areas which are small, plus they might be doing a boundary survey. So this is what we've come up with. The new plate coordinate, we have all the states have zones, but you can see that some of the states are going to have layered zones. Some of them don't want layered zones. Some of them are going to just have 1 zone. Some are going to have more than layered zones. They're going to have 3 layered because they want to go down to a smaller area than they have special needs for something. But this is the design that we're going to have right now. And as you can notice that Hawaii switched from the 5 zones to the 1 zone. So this is what we have in the state plane coordinates of 83, the design and the distortions that we have for each island. As you can see, it's pretty well distorted when you get up in the mountains, but in the low-lying areas, it's pretty accurate. But by changing it to a 1 zone, you can see that the distortions have gotten better or less. And this will be for the islands. And we know that in Hawaii, the big island, they're going to have multiple zones because of the vastness of the change in elevation that they have over on that island. So we skewed it to 56 degrees. And this will help the GIS users because this will be 1 zone. So why are we doing this? And this is how it shows up if we're doing this in Hawaii, in Honolulu. We have two marks that we have. We know the distance between them using the state plane coordinates, new values, and we know the state plane coordinates in the 83, the distance that we determine. And you can see that they're very close. The one's shorter than 0.05 of a foot, which is 10 parts per million. But the horizontal distance, as you can see, the true horizontal distance is closer to the state plane coordinates distance. And it's less than 1/1000th of a foot, and it's 2/200ths of a part per million. So this is going to make accuracy and the maps more accurate for the GIS users here. This is going to help with boundary surveys. It's going to help with tax mapping and other issues that we have, the needs that the state has. With that, there's something else that's going to go on that's completely different. Is that most people don't know that there are 2 feet that we use in surveying. There's the US survey foot and the new international foot. And the difference of them is 2 parts per million or 1/100th of a foot per mile. And you say, well, what's that? That's not really a big problem because we work in small areas and we're not going to see it. But later on, I'm going to show you how this problem is going to affect you and why you have to worry about it. So the surveyors use this conversion of it's this value, but I use 3.2808333333, which if you change it, that's what it'll be. And then the international foot. And why do you say that that's a problem? It will show later. But whose responsibility is for the standards? It's the other foot. It's the National Institute of Standards Technology, which is NIST, and the National Geodetic Survey. So we're working on this together for this standard. And what happened is Congress, originally in the Constitution, said that we have the power, Congress has the power to coin money and fix the standards of weights and measurements. So with that, we're being able to do this. But with this being said, this is to avoid the toothbrush problem. And this is something I learned from Michael Dennis. The trouble with standards is standards are like toothbrushes. Everyone agrees that they're desirable, but nobody wants to use someone else's. But without uniformity in standards, they are useless. And this is the reason why we're coming up to one standard of a foot in the country. And we're working with NIST on this. Why make the change? Well, that was the original intent was supposed to be done back 60 years ago. 2 feet is an inefficient and causes confusion, as everybody will see in a little while. It leads to errors and it costs money. It's absurd to have the same unit that differs by 2 parts per million. It defeats the purpose of having a length standard, but only recognized, and the 2 distance values are only recognized in part of the United States. And you'll see in the map next how it works. NGS is going to have software that can support backward and forward compatibility. And now's the time to change, because we're getting ready to do all these other changes with the 2022 datum. We said changing the foot is a trivial change to be made. And now what we mean is we're going to change to using the international foot, or the foot as some people are going to call it, when you get a product from NGS. So if you get a product that we have on our data sheets, or a conversion on the NAD transformation program, NCAT, we're going to use the foot conversion, or the international conversion only. We're not going to show the survey foot. So if it's in meters, the values in meters, we're going to convert to the foot only. And we know the survey foot problem is never going to go away, but we need to, if not, we need to address it. Or if we don't address it, it won't go away. But some states will want to keep it, but we'll be able to handle that, or they'll be able to handle that. But from NGS and the government, when they do a conversion, they're going to be using the international foot. So here's a map of the states and how the different ones and what conversion they use for feet. Alabama and Hawaii don't even have definition of what they use for foot, but I know in Hawaii, most of the surveyors use a survey foot. So you can see, if you're working in Arizona and you're going over to New Mexico and you have a project and you go in, you want to get values from New Mexico and they're converting everything using the survey foot, you're using international foot, you can run into problems. And this will help prevent chaos through the country. And here's where I'm talking about. Here's a conversion that we have that I did before. And we have the northing and easting in feet. We have US survey foot, international foot. And you can see that in the northing, the value of the feet is very, very close. It's 8 hundredths of a foot, but in the easting it's 3.9 meters. Now, I had a project that I was working on helping a surveyor do where this problem came up. They had gotten a GIS database from the Department of Airports, and they were resurveying and laying out the new striping for the airport, and they needed to lay it out. But when they went out, they did everything, and they worked in survey feet, and they tried to overlay everything, and they kept telling me, something's wrong with this GIS, or something's wrong with it. We can't overlay. We don't know who's right and who's wrong. So I took the data, and I analyzed it and looked at it. And when I converted things back, I just tried, okay, I'll take the feet converted back to meters, because we knew we had common points, to see what the meter value was, and I knew they used state plane coordinates and what theirs was. And what I found out is that the GIS that I got, that the airports had given the contractor, was done in international, the conversion was done in international feet, not survey feet. So I told them, take the GIS back, convert everything to meters and bring it back to survey feet. And when they did that, everything matched up. You could imagine if they hadn't done that, we would have had striping on the runway that could be off by 3 feet or 4, almost 3.5 feet, and that could be disastrous for the planes. So, like I said, there's a difference between the coordinate system and what you'll get when you're using international foot and survey foot. This is a change that you'd see in Arizona. It's between 1 to 5 feet. And if you're doing UTMs, it's between 23 to 27 feet. So if you're trying to overlay two projects, you could have problems. You wouldn't be able to see the difference. And in Hawaii, if the UTMs, this is the air is going to be up to from 15 to 17 feet. So these are issues that you have to take care of and be cognizant about. So if you have problems with your maps aren't lining up, you might want to find out if they're in feet. You might want to find out how the conversion's done. And most of all, after you do, put metadata so the next person doesn't have that problem. So how can I get prepared for the 2022 datum? Well, analyze your current workflow and procedures. See how you can how you're doing things so you can get your flow ready for the new datum. Create plans for adjusting future data collection, including if you have a contract, into the contract. And the data, maintain the raw data collected today for transformation into to the new datum for the future. And this is the biggest one, ensure proper metadata for all current data. If you know the metadata, we know what you have and what you're starting with, we can go from one to the other. But if you just say, here's the data, and you don't tell if it's a state plane coordinates, UTM, if they're feet, meters, or whatever, I've gotten projects like that. The only way I can decipher things is I just have to go down a checklist and figure it out. I didn't even know, where if I know where the work is, and I can try to figure things out. We have this problem in the Pacific with a lot of users. So metadata, metadata, metadata. And share the information with NGS so we can understand your agency challenges. If you have a problem, let us know in converting the raw data. We have experts that know how to do this. And if I'm not one that knows the answer, I will reach out to other people in our headquarters and they will help with that problem. So we can also get more information about this. I know I went over this quickly, but if you want to get more in-depth information, you can go to our website, geodesy.noaa.gov. And if you come down here on our webpage and go click on coming in 2022, the to datum, and you'll come up, and this page will come up, and you can read all the different backgrounds and what you want. So I'm just going to say, click on what to expect, and this page will come up, and it'll give you the maps of what I just showed, and it'll also give you a place where you can go to the blueprints of all the what's driving everything for this 2022 datum. You can get the blueprint that talks about the geometric coordinates. You can get one about the geopotential coordinates. And you get one with working with the new datum. Now this is very in-depth. They have a lot of formulas. If you're into formulas and all that, that's all information in there that you can get. Also, you can go back to the website, and if you come over to the left-hand side, you can see the state plane coordinates. Click on that. The state plane coordinate page will open up, and then you can go down and you can either download the design maps, you can convert coordinates, you can read on the final zones and all that, and the map will pop up, you can get the information. With that being said, I had this webinar set up a couple months ago, and we were knowing we were going to the 2022 datum, but with advents of what's happened with the furlough a couple of years ago and the coronavirus. We're not supposed to say that, the virus. We've had to delay the release of the 2022 datum. We were planning on releasing it by December 31st, 2022, but now we think it's going to be in 24-25 time frame. We're hoping for 24, but one of the big reasons why we can't release it is that we want to release everything together. We don't want to release the coordinates and then the geoid model. We want everything together, and we can't fly GravD at this time. We're behind on flying the GravD. We have about 81% done, but we can't, with the plane being grounded, we've only done part of Hawaii and part of American Samoa. We haven't done the Northern Marianas. And the plane we use is the one that flies into the hurricanes. So we can't use a plane between November or hurricane season to December. So we only have the plane for a very short time where we can get it, but other parts of the agency want to use the plane too. So we all have to fight for flight time. And to do that, to move to work in the Pacific, it's time and intensive. But with that, in summary, if you do geospatial work in the United States and the territories, and you work in the National Spatial Reference System, then every product you ever made, survey map, LiDAR point cloud, image, and DEM will have new coordinates in 4 to 5 years. And with that, I want to say mahalo and thank you. And are there any questions? And I hope it made sense.
Thank you, Ed. Yes, that I knew that I had heard that there was these delays had been publicly announced and described in at least detail. I hadn't heard yet that now it's hoping to be 2024, 25, but I'm glad that you brought that up at the end. All the information is still just as important. We just have a little bit longer to make the transitions with our data sets and our plans. There, a couple of questions have come in that Michael had addressed during this time. I think all of you can see these on your chat spaces or in your question space. One of the things that I was wondering if you could comment on, many of the faculty and students that connect with UCGIS and other universities don't have students that are necessarily going to get into this in depth and become geodesists. They end up relying on a lot of what the software prompts us to do, and options. You want to make informed choices, and some of the informed choices means that the options kind of need to be there. So how do you work? How does NGS work with software companies to make sure that there's some the options are as current as possible? I mean every, like, we had a question about people working with open source packages like GDAL, which would be used with R and others. Are there coordinated efforts around all of this, right? Maybe you could comment on that.
Yes, I'll take that. We've had summits over the last 3 or 4 years, not this year, but we've had summits, and one of the summits we had was that we had brought all the vendors that do GPS and GIS work, have programs or products, and we brought them in and we've explained this to them, and they're aware of these changes coming down, and we're hoping, and we're giving them guidance. They're asking us for guidance, and we're hoping they'll take our guidance and they'll be able to fix their programs. Or fix the program so they'll be able to handle these transformations. It's not our responsibility as NGS to do that. That's the private sector. We have our program that we have, and the reason why we have that program is because we need it for our needs for shoreline mapping and other issues that we have to maintain. So it's we always want to make sure we're not competing with the private sector.
Right.
With our product, but we have that product is for our needs and for internal NOAA needs for the Coast Survey and people like that are making nautical charts. Michael might be able to add more to it because he was involved in the forum with the GIS users.
Hi,
Michael?
yeah, Ed and Diana, can you guys hear me okay? I was
Yes,
muted.
we
Yes.
can.
Perfect, thank you. Yeah, no, Ed, actually, I think you answered it well. I just wanted to make sure folks listening to the webinar understand that, first of all, we're a government agency, so any software we produce is publicly available. Anyone can download our source code and use it. And we're getting better about making things shareable. At the very beginning of this presentation, Ed pointed out we're the oldest scientific agency. So you can imagine that some of our code is pretty old too. I mean, it's not as old as Thomas Jefferson, but it's old. I mean, a lot of our stuff is still in Fortran, for example, some very important programs that we use. So we're also updating that and trying to make things available as easily as possible in modern languages, and also providing our software's web services so it can be accessed and it's always directly and always be up to date. And like Ed said, we have been coordinating with industry to make sure they stay up to date and make sure that we can provide the things that they need to keep their software current. There's some really big challenges here, and I don't want to go on too long, but probably the most difficult one for the private software vendors is dealing with time-dependent transformations. The time part is really, really hard, and virtually no one on the commercial side is handling that appropriately. So that's a big challenge we'd like to address in the next few years as part of the release of the modernized NSRS.
Interesting. All right, yeah, I appreciate the comments about the fact that it's really on the vendor side to make sure that they're integrating the options that are suitable and is in the right timely manner. I had a related, anyone else, just we have a few minutes left. If you have a question, feel free to type it into the question space. Michael, I had a question, and maybe there's a quick answer for this, perhaps. It was really interesting to me to think that there would be these statewide state plane coordinate systems, because one of the things that introductory GIS teachers would always cover is why there would have been different projections chosen for the zones, you know, around between California versus Tennessee. I mean, states, the way their own geography happens to be aligned. Can you just comment quickly on how, if there is just one state plane coordinate system for California and one for Tennessee, again, how does that? It just must be averaging out the necessary distortions?
Yeah, that's basically it. So a little background about this. Actually, there are a few states that have a single statewide zone, even though they're very large in current state plane. For example, Montana. Montana had 3 zones for state plane 27, but has 1 for state plane 83. And when we started this project, we asked people what they wanted, and we got their input, and a very large proportion were super enthusiastic about having a single statewide zone, and that's mainly for statewide GIS applications, say like a Department of Transportation or any state agency. So you take a state like California that has 6 zones, state plane 83, it'll still have multiple zones, but every state, California included, Texas included, even Alaska, will also have a single statewide zone, so they have a single consistent geometry for the whole state. But again, most states will also have smaller zones as well to get the coordinates that have less distortion, as Ed was talking about earlier, for other applications. But again, what kind of caught us by surprise. It was a super popular idea, so we embraced it and made it part of the system.
Okay, so
Let me add one other thing, and
yeah.
this might be helpful for people listening. It turns out that there is one state in state plane 83 that has 2 layers, and it's Kentucky. Kentucky has 2 state plane zones that people might be used to, but also has 1 state plane zone for the entire state at the same time. So it already exists in state plane 83, and that's kind of the model we're using to go forward, so more states can have that.
Interesting. Excellent. Any final questions? Someone want to type something into the question space? Otherwise, we had a question about this presentation being available. It has been recorded, and we'll make sure that the link to the recording is processed and put up on our website. The slide deck itself will also be provided to participants. And I know that, or on our website, really, to not just participants, to the public. I know that this is going to be something that will be very useful for people as they're trying to understand some of these details and integrate this knowledge into their instructional activities. So thank you both very much for your time and sharing this important information. Even if we're in a situation where it's getting delayed a little bit, it's just as important to start to understand it now.
Well, hey, Diane, I had, and I see there's still a couple questions coming in. I could take a moment just to address it real quick verbally, since I'm not a very good typist, actually, so I struggle, especially talking and typing at the same time. David Rossiter, if I say his name correctly, he's asked quite a few questions, and he's brought up a thing that's coming up more and more often, and we already talked about some, is about making our software more formally part of the open source community. There's a process for that, right? And I don't know how far we've gone down that path. I'm not in our division that does that. I think we're making more and more progress. So we're aware of that, trying to make things as shareable as possible. And also, I want to point out, he had said we can only being able to do one coordinate at a time by our API, but there is actually there is a multi-point conversion capability in NCAT. I just want to make sure people know that you can do thousands and thousands of points at once. So just so everybody knows, with NCAT by uploading a small file. So there's that. And there's another question came in from Richard Day. Will the new term be NSRS 2022? This is a good question. So will the new term be NSRS 2022 to replace both NAD XX and NAVD XX? We'll call it that. There is no overarching term for the whole thing. For example, Ed had mentioned there's going to be 4 terrestrial reference frames. There isn't one term just for those 4 frames, which I'm not sure I'm that happy with, but that was the decision. So people have started, even internally, we've started saying NSRS 2022 for the whole package, but that's not official. Right now, we just say Modernized National Spatial Reference System. So there is kind of a branding thing here, and not a single name for those 4 terrestrial reference frames, for what it's worth.
We'll have to see what, NAD 83 and has become such a standard thing to be able to describe over the years. We'll have to see what settles out and how people begin to reference this.
Yeah, so people in the conterminous United States, or well, all of North America, will probably use NatRef 2022. So that would be the replacement for NAD 83. Oh, and just so we're clear, it is already kind of complicated. There are actually 3 NAD 83 frames simultaneously. There's one for North America, one for the Pacific Plate, and one for the Mariana Plate. Now, people just say NAD 83, but really there's 3 different ones, and they are different. So part of that is just perception and history. Why call Guam North America? It doesn't really make sense, but it inherited that name because of the way things have evolved over time.
Right.
And can I say one thing? I've just put up a slide from our webpage, and people, if they want to know, they can subscribe to the email for notifications, and that way, if they do that, they get on the listserv. So every time we make a change or we come out with something, we have like the slide that I showed that showed our modernization news. You'll get that, and it'll come up with all of what's changing and what we're calling it and different things like that. And I highly recommend that people do that so they can stay abreast of what the changes are and what's coming about.
Good to know. All right, thank you. We've just gone over the top of the hour. I want to thank again our presenters, Ed Carlson and Michael Dennis. Thank you so much for your time. Thank you, UCGIS audience and the rest of the world who signed up for this webinar. Stay tuned to our website where you'll see more information about other webinars that we'll be announcing soon. We're going to have a very busy schedule over the next 6 to 8 months. So thanks again, everyone. Take care and be well.
Thank you, Diana. My pleasure.
Bye-bye.
Thank you.
Bye-bye.
Bye-bye.